exceptionally brilliant youth. Subsequently, it will be for the same work that he is awarded the Nobel Prize. If Planck is the father of the theory, Einstein is a parent who nurtured it. But, like all offspring, the theory then went its own way, unrecognized by Einstein himself. In the second and third decades of the 20th century, it was the Dane Niels Bohr who pioneered its development. It was Bohr who understood that the energy of electrons in atoms can only take certain values, like the energy of light, and, crucially, that electrons can only jump between one atomic orbit and another with fixed energies, emitting or absorbing a photon when they jump. These are the famous quantum leaps. And it was in his institute in Copenhagen that the most brilliant young minds of the century gathered together to investigate and try to bring order to these baffling aspects of behavior in the atomic world, and to build from it a coherent theory. In 1925, the equations of the theory finally appeared, replacing the entire mechanics of Newton. It's difficult to imagine a greater achievement. At one stroke, everything makes sense, and you can calculate everything. Take one example. Do you remember the periodic table of elements devised by Mendeleev, which lists all the possible elementary substances of which the universe is made, from hydrogen to uranium, and which was hung on so many classroom walls? Why are precisely these elements listed there? And why does the periodic table have this particular structure, with these periods, and with the elements having these specific properties? The answer is that each element corresponds to one solution of the main equation of quantum mechanics. The whole of chemistry emerges from a single equation. The first to write the equations of the new theory, basing them on dizzying ideas, would be a young German of genius, Werner Heisenberg. Heisenberg imagined that electrons do not always exist. They only exist when someone or something watches them, or better, when they are interacting with something else. They materialize in a place with a calculable probability when colliding with something else. The quantum leaps from one orbit to another are the only means they have of being real. An electron is a set of jumps from one interaction to another. When nothing disturbs it, it is not in any precise place. It is not in a place at all. It is as if God had not designed reality with a line that was heavily scored, but just dotted it with a faint outline. In quantum mechanics, no object has a definite position, except when colliding headlong with something else. In order to describe it in mid-flight between one interaction and another, we use an abstract mathematical formula which has no existence in real space, only in abstract mathematical space. But there is worse to come. These interactive leaps with which each object passes from one place to another do not occur in a predictable way, but largely at random. It is not possible to predict where an electron will reappear, but only to calculate the probability that it will pop up here or there. The question of probability goes to the heart of physics, where everything had seemed to be regulated by firm laws which were universal and irrevocable. Does it seem absurd? It also seemed absurd to Einstein. On the one hand, he proposed Heisenberg for the Nobel Prize, recognizing that he had understood something fundamental about the world, whilst on the other, he didn't miss any occasion to grumble that this did not make much sense. The young lions of the Copenhagen group were dismayed. How was it possible that Einstein should think this? Their spiritual father, the man who had shown the courage to think the unthinkable, now retreated and was afraid of this new leap